Hi, in this video for section 2.8, we will discuss the first two objectives. We will define a syllogism, and we will draw Euler diagrams to represent a syllogism. So for the first objective, to define a syllogism consists of two or more premises followed by a conclusion. Typically, the syllogism contains at least one quantifier. So now the first key thing is to be able to distinguish a syllogism from an argument. Now, we've discussed arguments in previous sections. So a syllogism and an argument are super similar. It's just that the syllogism contains the quantifier, at least one quantifier, and an argument does not contain any. Further, syllogisms tend to follow kind of like a pattern, tend to follow this rhythm. As you see more examples, you'll get used to that. Whereas arguments don't, right? Arguments have a rhythm of their own. So for example 1, are the following strings of statements arguments or syllogisms? Why? So 1a, no unicycles have two wheels. I have a unicycle. Therefore, my unicycle doesn't have two wheels. So this is a syllogism. It follows the general pattern that syllogisms do. So it is a string of statements. That string of statements contains a quantifier, right? And it consists of two premises and a conclusion. So that is a general syllogism. So B, all zoos have animals. So already I hope you're thinking, oh, I see a quantifier. This might be a syllogism. Let's read the rest of it. Joey goes to the zoo today, or Joey goes to the pool today. Joey did not go to the pool. Therefore, Joey went to the zoo. So this actually is an argument. I know the first statement contains a quantifier, right? All zoos have animals. But it's really irrelevant to the rest of the strings of statements. So the rest of the argument follows the form of disjunctive reasoning. So it actually is a valid argument. That first sentence is just irrelevant. Okay, so the next thing we need to talk about is how do you prove a syllogism is valid or invalid? Before we get to that, let's remember what we did with arguments. With an argument, we would build a truth table or compare it to a general form of argument that we already know is valid or invalid. Right, but our first approach was drawing a truth table. So let's think about drawing or making a truth table for a syllogism, for like 1a, for example. So how would you make a truth table for the statement, no unicycles have two wheels? It doesn't really make sense to make a truth table anymore. At least I don't see right away how to make one. So therefore, we need a new approach, a new method to show that a syllogism is valid or invalid. That new method is actually going to be Euler diagrams. We talked about those earlier in the chapter. And we will use Euler diagrams to represent the statements. And then you can read that Euler diagram to prove the syllogism valid or invalid. So recall from earlier in the chapter, an Euler diagram looks like a Venn diagram, but it's a way to show relationships between different characteristics or between different objects. So this table comes straight from your book. I want to take a moment to talk you through this table. So it is Euler diagrams to represent statements. So these four statements are kind of general forms of statements you might see in a syllogism. So let's start with all A are B. So all A are B. Already I'm thinking all of the A's must be inside all of the B's. all of the A's are inside the B's. So this is kind of the first way you could draw that, where all of your A's are inside all of your B's. Kind of a special case or an exception is when A is the same thing as B. So here all your A's are still inside all of your B's. For no A, R, B, here I'm thinking like all A's, well, I guess here I'm thinking there's no overlap between A and B. Because no A are B's, right? So none of your A's can be inside your B's. So then we get this case here where there's no overlap, and that's the only way to draw an Euler diagram to represent that statement. Some A are B, there's a whole bunch of ways to draw an Euler diagram to represent that statement. So this is kind of the first one mathematicians think of, is that there's some overlap between A and B. So in this case, these would be the A's that are B's, right? That overlap there. So mathematicians think next, okay, what else could this look like that some A's are B's? It could look like this second case. So here, the A's that are B's are actually these ones inside here, right? And these are the A's that aren't B's, the ones out here. So there's also two special cases here, and these both happen to be where all A are B, these last two. So if all A are B, well, that means some A are B, right? This is just kind of like a stricter case of some A are B, where all A happen to be B. So these two work as well. Again, these two are kind of a special case to some A are B. Some A are not B. So here I'm thinking that there are some A's outside of the B's. So the first way you could draw this is actually the same as some A are B, right? Some A are not B. That would just be these A's out here now that are not B's. It could also be the case that no A are B, right? This is kind of a stronger case, but that's okay. That still means that some A are not B. Or it could be something like this. So some A are not B, and these would be the A's that are not B's. Okay, so in our text, and in most of the texts that discuss this subject, we typically use the yellow column here. So in our next example, I will say draw all possible Euler diagrams to represent the statement. And technically, it's all of these that you see, right? But kind of to simplify things, or otherwise this will get really out of hand real quick. So to simplify things, we'll just default back to this yellow column. Okay, let's do example 2 to wrap up this video. So draw all possible Euler diagrams. Remember, we'll default to that first yellow column to represent these statements. So let's consider the first statement A. Some twins are not identical. So this, if we rely back on our table, some twins are not identical. This falls into the last option, right? Some A's are not B's. So we could draw any of these three to represent that statement. Let's just do the first one as kind of our default. So some twins are not identical. So that means that these would be your twins, and these would be your identical twins. Identical twins. Now, as kind of a side note, and this happened here, you might say, well, wait a minute, this diagram doesn't really make sense, because like what would be over here? What would be an identical twin that isn't a twin? Well, that doesn't make sense. So sometimes this happens, that the first diagram you draw, while it works technically for statement A, it just doesn't really fit. So really what we could draw to fit, and the one that would make sense here, is actually this third one here. And this is because all identical twins are twins, right? It just so happens that there's other kinds of twins too. So really the diagram could also look like this, that here's your set of twins, and then here on the inside is those twins that are identical. And still this diagram works for this statement, some twins are not identical. Those would be these twins out here, right? But really, in the reality of this statement, this diagram makes more sense than the first one. That's kind of a side note, right? We'll draw the first one and say, yep, that's my default diagram. Realizing that in some situations, right, this one might make more sense. And they are both valid diagrams to represent statement A. All right, no winters in Florida have multiple feet of snowfall. So this falls under the no ARB. So we want no overlap, right? No winters in Florida have multiple feet of snowfall. So this first circle would be winters in Florida. And your second one will be winters with multiple feet of snowfall. And we have no overlap. If I could spell multiple. Winters with multiple feet of snowfall. Okay, and no overlap. Cool. So that concludes example 2, and that concludes this first video for this section.